previous videos, we've talked about the fact that most reactions are actually multi-step reactions, and that the rate of an overall reaction with several elementary steps will be determined by the slowest of those elementary steps. If the first elementary reaction is the slow one, determining the overall rate law is easy. It's just going to be the rate law for the first elementary reaction. So here's an example. We have this reaction. The overall reaction is nitrogen dioxide plus carbon monoxide reacts to yield nitrogen monoxide and carbon dioxide. Pretty simple. It has two elementary reactions as shown here. The first elementary reaction is the slow one. Even though the rate law that would be predicted for our overall reaction, if we could do it stoichiometrically, this would be K times the concentration of nitrogen dioxide times the concentration of carbon monoxide. This is not the rate law for this reaction. The rate law is determined by the slow step of this two-step reaction, and it is K times the concentration of nitrogen dioxide taken to the second power. And we got this directly from the stoichiometry. We have two molecules of nitrogen dioxide. This is a bimolecular reaction, so our rate law will be second order. But what if our rate limiting step is not the first step? Take a look at this reaction. Our overall reaction to nitrogen monoxide plus chlorine reacts to form two molecules of nitrosyl chloride. Also notice that this is an equilibrium reaction, which is a little different than what we've seen before. In this two-step reaction, rate 2 is our slow step. It's our rate limiting step. Now, if we were to use stoichiometry to determine the rate law, our rate law would be K times the concentration of NOCl2 times the concentration of nitrogen monoxide. But there's a problem here. NOCl2 is an intermediate, and we can't have intermediates in our rate law. Think about this. Intermediates are unstable, they don't last very long, and it's hard or impossible to measure the concentration of them. So we have to use other methods to estimate or approximate our rate law. To deal with situations like this one, we're going to use a simplified version of something called the steady state approximation. We're going to take advantage of this observation. In a reversible reaction, a reaction that's at equilibrium, the rate of the forward reaction is the same as the rate of the reverse reaction. And we haven't done equilibrium yet, but this is a definition of equilibrium. Equilibrium is typically denoted by this double arrow here. Well, we can write this out. Rate forward equals rate reverse. And we can substitute in our forward rate law and our reverse rate law so that we get something like this. K1 times the concentration of nitrogen monoxide squares equals K to the -1. We're using that little -1 subscript to denote that it's the reverse reaction, and we're multiplying that K by the concentration of N2O2. We can manipulate this equation algebraically to get a hypothetical concentration of an intermediate. In terms of reactants, we can actually get the concentration of. So in this example, we're going to divide each side by K sub -1, and we're going to flip this equation around so we have the concentration of our intermediate on the left, and we get this equation here, where we have K1 divided by K sub -1 multiplied by the square of the concentration of nitrogen dioxide. And if we wanted to, we could combine these individual constants to form a third constant, which we could call K3, and thus simplify our equation a little bit. So just to recap, if the first elementary reaction is not rate limiting, we can use this steady state approximation to find a rate law expression that's written in terms of our reactants, which we can measure and find the concentrations of, instead of in terms of our intermediates, which we can't measure the concentration of. Now let's go back to our original two-step reaction with the slow step being the second step. When we take a look at step 2, we notice that it is the slow step, hence it's the rate limiting step. And though one would predict the rate law would be this rate, K times the concentration of NaCl2 times the concentration of NO2, it has an intermediate in it, and this is not allowed. So to determine the rate law for this reaction, we need to be able to express the rate law in terms of our reactants with no intermediates. And we're going to use algebraic manipulation just like we did previously. From step 1, we can find the rate for the forward and reverse reactions. So the rate of the forward reaction equals K1 times the concentration of nitrogen monoxide times the concentration of chlorine. The rate for the reverse reaction is K sub -1 times the concentration of NoCl2. Now, because step 1 is in equilibrium and the forward and backward rates are equal, we can set our forward and reverse rate laws equal to each other, like this. Now, for our second step, we're going to find the rate law for step 2, which is this one. Rate equals K2 times the concentration of NoCl2 times the concentration of NO. We can use algebra to derive the concentration of NoCl2, the intermediate, in terms of concentrations that are not intermediates. Make sure to keep track of the different constants because they are very important. Do not lose them. We can use good old-fashioned substitution to substitute our new expression into our rate equation for step 2. And this is going to give us the rate in terms of the concentrations of the reactants. And then we can simplify this into a form that's easier to work with. And if we want to, we can define a new combined constant K3, where K3 equals K1 times K2 divided by K sub -1. Let's summarize. If the first elementary reaction is not rate limiting, approximations such as steady state must be made to determine a rate law expression.